Welcome to this explainer. If you've ever stared at a dense wall of sines, cosines, and tangents and felt that sudden wave of absolute panic, hey, don't sweat it, you are in exactly the right place. Today, we're taking a chaotic, complicated wall of mathematical notes and translating it into clear, easy-to-use tools. By the end of this, you're going to be able to calculate absolutely any angle with confidence. We're turning chaos into a totally predictable logical system.
Okay, let's quickly map out our journey for today. First, we'll be decoding the math wall itself. Then, we dive into the fundamental ASTC quadrant rule. After that, we'll master trigonometric identities, work through some step-by-step angle calculations, and finally, we'll give you a chance to try it yourself.
Section 1, Decoding the Math Wall, Unlocking the Secrets of the Source Material.
We're diving right into the deep end today. And what's wild about the source material we're decoding is that while it looks completely overwhelming, literally edge-to-edge white scribbles, floating equations, and graphs, it's actually just telling a really simple, repetitive story about circles and triangles. You know, math has this funny habit of hiding very basic universal patterns behind a wall of intimidating notation. But everything we're looking at ultimately boils down to a few core, unbreakable rules. And the great news, once you see the underlying pattern, you can completely ditch the rote memorization. You really don't need to memorize 100 separate equations. You just need to understand the basic rules of the math.
Section 2. The ASTC quadrant rule, the geographic map of trigonometry.
To really make sense of all those numbers, we've got to understand the fundamental rule that governs basically every single calculation you will ever do in trigonometry. We're talking about the ASTC rule. Think of this as a spatial shortcut. Better yet, think of it as a literal geographic map drawn right onto a standard XY coordinate plane. Imagine the coordinate plane is a sprawling city, divided into 4 distinct districts, or quadrants. Just like different neighborhoods have different rules, each of these quadrants is ruled by specific trigonometric functions. Because whenever you calculate an angle, the ultimate question you're trying to answer is always, is my final number going to be positive or is it going to be negative? The ASTC rule is the absolute key to answering that.
Let's break down those 4 distinct zones. Starting in the top right, quadrant 1, the letter A stands for all functions being positive. So if your angle lands here, it doesn't matter if it's sine, cosine, or tangent, the answer is positive. Now, moving counterclockwise over to the top left, we enter quadrant 2. Here, the letter S tells us only sine is positive. If you try to calculate a cosine or a tangent in this specific neighborhood, bam, the answer's negative. Moving down to the bottom left, quadrant 3, the letter T means only tangent is positive. And finally, swinging over to the bottom right, quadrant 4, the letter C means only cosine is positive. A lot of students remember this journey with the classic phrase, all students take calculus. It's an incredibly elegant rule, and it gives you the ultimate foundation for knowing exactly what sign to put in front of your final answer.
Section 3, Mastering Trigonometric Identities, Translating Big Angles into Friendly Numbers.
So with our ASTC map securely in hand, we need some translators. These identities act as essential mathematical bridges. They take scary, incredibly large angles that land way over in quadrants 2 and 3, and they translate them back into friendly, familiar, bite-sized angles from quadrant 1. And the way they pull this off is usually by anchoring the math around the 180-degree mark. Now, you might be wondering, why is 180 degrees such a magic number? Well, it's because when you use 180 to bridge your angle, the mathematical function itself stays exactly the same. Sine stays sine, cosine stays cosine, tangent stays tangent. It literally eliminates half the mental math you have to do. You keep the function the same, and then you just tack on a positive or negative sign based entirely on that ASTC map we just talked about. In quadrant 2, only sine stays positive. In quadrant 3, only tangent stays positive. It's just a brilliantly logical system.
Section 4, Step-by-Step Angle Calculations, Applying the Rules to Real Problems.
Okay, time to prove that this actually works in practice. This beautifully illustrates the inherent elegance of math. There isn't just one single rigid way to solve a problem. Let's look at finding the sine of 135 degrees. You can actually use 2 different paths here. Path 1 relies on the 90-degree identity, so sine of 90 plus 45 degrees forces the function to flip, turning it into the cosine of 45 degrees. Or you can take path 2, using that super friendly 180-degree identity we just praised. Sine of 180 minus 45 simply becomes the sine of 45. The function doesn't change. Now, pause and think about the quadrant. 135 degrees is right there in quadrant 2. And what do we know about quadrant 2? Under our ASTC rule, sine is always positive. Because of this, both mathematical paths confidently lead you to the exact same universal truth, a positive 1 over the square root of 2.
Let's try another one. If we're calculating the cosine of 150 degrees, we see those exact same two paths open up again. Path 1 uses 90 plus 60 degrees. Because we're starting with cosine and crossing that 90-degree threshold, the identity makes it flip into a negative sine of 60. But path 2 uses 180 minus 30 degrees, which keeps the function exactly the same but becomes the negative cosine of 30. Now ask yourself, why on earth are they both negative? Well, just refer back to your map. Where does a 150-degree angle live? Right in quadrant 2. And the all students rule reminds us that only sine gets to be positive there. So any cosine calculation in that district absolutely has to be negative. Both paths reliably land us at the correct destination, negative square root of 3 over 2.
Let's push into brand new territory and systematically break down a slightly trickier angle, the cosine of 210 degrees. We'll do this in 4 simple steps to prove you really don't need a calculator for this stuff. Step 1, identify the territory. 210 degrees pushes past the 180-degree line, dropping us straight into quadrant 3. Step 2, consult the map. ASTC. All students take calculus. In quadrant 3, take stands for tangent. Since only tangent is allowed to be positive here, we instantly know our cosine calculation is going to be negative. Step 3, apply your bridge. We use that friendly 180-degree identity. Cosine of 210 is exactly the same as the cosine of 180 plus 30. And finally, step 4, solve it. The 180 drops away, leaving us with a negative cosine of 30, which universally equals negative root 3 over 2. You know what's incredibly satisfying about this process? It's seeing how that exact same quadrant 3 logic strictly applies to the other functions for that exact same 210-degree angle. Check out the tangent of 210. It translates to tangent of 180 plus 30. Since tangent completely rules quadrant 3, the result remains a positive tangent of 30, giving us positive 1 over root 3. But now look at the sine of 210. Sine of 180 plus 30. Sine definitely does not rule quadrant 3, so it gets forced into a negative sine of 30, cleanly giving us negative 1/2. See how perfectly this works? It aligns with our ASTC map every single time. You aren't just guessing, you're applying a totally foolproof system.
Section 5. Try it yourself. Testing your new mathematical tools.
All right, we've successfully scaled the mountain. That incredibly intimidating wall of math we talked about at the start, it's really no longer an obstacle. It's just a map. And now you know exactly how to read it. Our source material has a great list of specific practice problems. And the truly empowering part here is that you now possess every single tool required to solve them. You don't need the final answers just handed to you anymore because you actually understand the underlying process.
So I'm leaving you with a direct challenge. Armed with your ASTC quadrant map and your friendly 180-degree translators, can you calculate the tangent of 240 degrees? Think about which quadrant it lands in, who rules that specific quadrant, and what your bridge angle is. But honestly, more importantly, the next time you face a massive wall of intimidating information, whether that's advanced math, crazy complex data, or just a really difficult problem in life, ask yourself, what is the underlying map here? Once you strip away the noise and find your own set of base rules, is there any wall you can't decode? Thank you so much for joining me on this explainer, and keep looking for those hidden patterns.